Hey guys. So last time we were able to determine an equation for delta h, the error in the height measurement of some sort of object, in that case your girlfriend, using trigonometry, specifically tangent. So we were able to come up with this equation right here. So now we're going to make things one step a little bit harder. And this is to say, okay, we can find delta h, but if we're given some parameters delta d and delta theta are errors that we just can't change, how far away from the object should we be so that we can measure the height of the object as accurately as possible? So for this entire derivation, we're going to assume two things that should be kind of intuitive. First is that delta theta is much less than theta, as in for the angle that you're measuring, your error is not going to be of the same magnitude or anywhere near that. Same thing with delta d. So this just means that you're measuring things competently. So the first thing we can do is we can take the equation for delta h and make things a little more simple. We see here we have tangent, tangent, and tangent squared. And in any kind of derivation like this, what you should aim to do is to get rid of trigonometry terms that are going to be really difficult to deal with. Well, we know that h equals d tangent of theta, obviously. So we can rearrange that to say that tangent of theta is going to be equal to h over d. We can then substitute this guy into that equation, and let's see what we would get. So we'll have that delta h is going to be equal to d delta theta plus delta d times h over d now, plus d delta theta times that thing squared, which will become h squared over d squared, all over 1 minus delta theta times h over d. Well, this d will cancel out with this 2 right there, so we can simplify this thing up a little bit. But this is not exactly all that simple. What we can do is we can multiply this denominator through so that we'll have, we can get rid of this over d term on the top and the bottom. So if we do that, we get the delta h is going to be equal on the bottom, and that's going to be equal to d minus delta theta times h, just multiplying through the bottom by d. On the top we have to do the same thing, so it'll give us delta h is going to be equal to d squared delta theta plus delta d h, plus over here that's going to get rid of this d also, so it'll become delta theta h squared. So just as a quick recap, this equation and this equation here are identical. We just made one simple substitution and played around the equation a little bit. All right, what we can do now is, since we're trying to optimize this, is to play a little trick. So we can take dummy values, if you will. Dummy values in the sense that we can estimate, we can do this by guessing numbers for some of the variables and then solving for just one single variable at a time, and then retracing our steps to draw some sort of better conclusion. So for this, we're going to assume that our delta thetas and delta d's are going to be equal to 0.1 meters for delta d, and for delta theta, it's going to be equal to plus or minus 1 degree. For these kinds of calculations, though, you have to use radians and not degrees. And this is a key point, because degrees have units, degrees. Radians, on the other hand, do not. So once you plug things into this equation up here, you need to get out a delta h, which is in meters, not meters times some sort of degree measurement. It has to be a unitless measurement, so therefore radians. Okay? All right. So then if we do that, we have values for delta theta, delta d, delta theta, and delta theta down here. We're left with d's and h's. What we can then do, and this is the key to this entire thing, is to set h equal to something. The height in this case, like the height of the object that you're going to measure, isn't going to be changing. It will change across different cases. However, once you have an object, its height is not going to change. Your girlfriend is not going to go through a growth spurt as she's standing there unless she's really creepy. So what I've done here is taking these two values for delta theta and delta d in this equation, I've chosen various measurements of h. So saying that, okay, let's say h was 50 meters, 75 meters, etc. What I then was able to do was plug those values into this equation. That leaves a delta h over here, it's like your y if you will, and d's over here, which is like your x. So you have y's and x's, you can plot the function. So for each value of h, what you will get is a function that looks somewhat like this. And this is going to be delta h right here. On the bottom here you have d, and this is going to be delta h. So this is the error in the height measurement as a function of how far you are from the object. And we see that with each equation we have, we're going to have some sort of minimum here. It corresponds to some sort of d minimum. We can then record these values for each h that we pick. So for example, for this one here, I set h equal to 50. Since we already have values for delta theta and delta d, we can solve for the minimum graphically using some sort of graphing calculator. Just by inputting this equation, we can solve for a d minimum, which we then record over here. What we can notice is that if we do this a bunch of times, we see a pattern, right? Because we see that the h's and the d minimums are really close to each other. Like they're almost the same. The percent deviations between them are really low, actually. So what that implies is that h is going to be approximately equal to d tangent of theta, where d here is the minimum d. That's how far we want to stand from the object at all times. So we can say that h is going to be approximately equal to d minimum, d min standing for d minimum, times tangent of theta. Well, for this to be true, that means tangent of theta must be kind of equal to 1, right? So this means that tangent of theta is going to be approximately equal to 1, or, oh sorry, tangent of theta is approximately equal to 1, or that theta is going to be approximately equal to 45 degrees. And that there is kind of our answer. What this means is that for us to get the most accurate measurement possible, we want to stand far enough from the object such that the angle of incidence between the ground and the height of the object is going to be 45 degrees. In other words, we want it so that if this angle is 45 degrees, we want to stand at approximately one height of this away. So we have h and we have d. We want to stand such that d is approximately equal to h. Since you can't really do that on the first go outside, just make sure that your protractor is going to be about 45 degrees up. And that's how you can get the most accurate measurement. This one was a pretty quick derivation, and it takes a few times to get used to it. So if you want to, rewatch this video a few times, and then try doing this yourself on your own graphing calculator. It isn't that hard. It does take a lot of equations to input, but it doesn't take that long. It took me less than 10 minutes. So yeah, good luck with the lab, and I'll see you guys next time.